Okay, so here's what I'm going to do. So if you just want to pay attention to this, okay. We've talked about the idea that even though there's a probability density function for the normal distribution, so in other words that 1 over 2 pi, root 2 pi times by sigma, e to the negative x minus mu all squared, all divided by 2 sigma squared, we're never going to use that formula. Not in this course anyway, okay? It's pointless, okay? We're not going to work out the probability that x is equal to some particular value. Instead, what we're going to look at, and we've just spoken about this, we're going to look at cumulative values instead. Okay, let me just quickly check this recording. Yeah, we're all good. So, we're going to talk about cumulative values instead. So, let's just remind ourselves. What goes in the middle of our normal distribution? Mu. Okay? And you notice that normal distribution has to be symmetric. Okay, so that's a really important feature. So it has to be symmetric. And we saw that with our balls dropping. Okay? Things which were happening on the left were pretty much identical to things which are happening on the right. Okay? So, let's divide this up. So let's say this is mu plus 1 sigma, mu plus 2 sigma, and then mu plus 3 sigma. And likewise on the left, we've got mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. Can I ask you to make a copy of this? So, I said that with the normal distribution, it makes much more sense to deal with cumulative values. And the way which we deal with the cumulative values is knowing the percentage or the proportion of the data that we've had up to a particular point. So cumulative will always mean moving from the left. Okay, so f of x, f of x will always be equal to the probability that x is less than or equal to that particular value. Okay, that's what f of x literally means. Okay, so in other words, if it's less than or equal to, we're talking about values from the left moving up to that point. Okay, so I know the percentage of my data from empirical studies or whatever you might want to look at. I know from empirical studies the percentage of my data which I should have had up until this point here. In other words, 3 standard deviations below the mean. And you can see on the board there, it's about 0.15%. Okay? So I know there's going to be about 0.15% of my data which falls in this little region in here. Okay? So everything up until 3 standard deviations below the mean. Not a lot of my data. Okay? Then if I look at my next region, so if I look between 3 standard deviations and 2 standard deviations below the mean, I know that it should be about 2.35% of my data in that region there. Okay, so between 2 and 3 standard deviations below the mean. Okay? If I look at the percentage of my data between 2 standard deviations and 1 standard deviation below the mean, I know it should be about 13.5% of my data. Okay? If I look sort of between 1 standard deviation below the mean and the mean itself, I know that 34% of my data should lie in this region. Okay? How much of my data should lie between this mean and 1 standard deviation above the mean? Absolutely, because I know it's symmetric. Okay? And how much of my data should lie between 1 standard deviation and 2 standard deviations above the mean? 13.5%. How much of my data should lie between 2 and 3 standard deviations above the mean? 2.35. And how much of my data should lie above 3 standard deviations above the mean? Absolutely. So does that make sense? The way which we deal with the normal distribution is no longer with the probability density function. In other words, the probability that x is equal to some particular value. The way in which we deal with it instead is by looking at this, the cumulative distribution function. In other words, because we know from empirical studies, from evidence, the amount of data that we should expect between each of these individual regions, we should then be able to work out everything that we need. Okay? So, you notice that everything underneath the curve should add up to what? 100%. That makes sense? So everything underneath the curve should add up to 100%. Okay? So, let's have a look at some of these questions then. Particularly, let's have a look at question 1. Okay? So question 1, we've been given a normal distribution. So a random variable is distributed normally with a mean of 4 and a variance of 9, or variance of 3 squared. Okay? You notice the number that goes there is always the variance in this course. You happy with that? Always the variance. So for part A, we've been asked to find the probability that x is less than 1. Okay? Well, let's think about this curve. Let's literally draw this curve out a little bit smaller. Okay? What value is the mean? 4. Okay? What value is one standard deviation above the mean? 7. Because the standard deviation in this case is 3. And I know that one step above the mean is going to be the mean plus the one standard deviation. That make sense? What about another standard deviation? 2 standard deviations above the mean? 10. What about 3 standard deviations above the mean? 13. What if I went the other way? So what about one standard deviation below the mean? 1. What about one standard deviation below the mean again? Negative 1, right? Yeah? No, negative 2. What about one standard deviation above the mean again? Negative 5. Good. Does that make sense? Yeah? So literally think about these things as steps above and below the mean. Steps. Okay? Where a step is one standard deviation. Does that make sense to everyone? Yeah? Good. Okay. So if I want to find the probability that x is less than 1, okay, I'm looking at everything up until that point. Okay, I'm looking at everything up until that point. So in other words, I know that I'm looking up until one standard deviation below the mean. Okay, so it's going to be 0.15 plus 2.35 plus 13.5. How much percentage is that? What's that equal to? 16%. Just literally adding those together.
Why added 1? Add 13.5. It's less than 1. X less than 1. So we added 1.
So basically, I'm looking at all of my data up until that point there. Okay.
Because it's continuous, so it's the same. Yeah?
Exactly. It's less than or equal to 1 as well. It doesn't matter whether it's less than or equal to 1. Absolutely. Yeah. That's a really good point. Yeah. And I need to emphasize that. I can't emphasize that enough. With a discrete distribution, it matters whether it's less than or equal to. With a continuous distribution, it doesn't. Because you want everything up until, technically a little bit below 1, but actually it's including 1 in this case as well.
But it's not mentioned, so we have to...
Sorry?
It's not mentioned that it's discrete.
It is because it's a normal distribution. Yeah, because I've given you it's a normal distribution, you have to assume it's a continuous distribution. Yeah? But you're happy with how you work out the probability? Yeah? Okay. What about part B then? What about the probability that x is greater than 10? Okay. Well, x is greater than 10 corresponds to 10 corresponds to 2 standard deviations above the mean. Does that make sense? 2 standard deviations above the mean. So therefore, I'm going to be looking at 2.35 and 0.15. Which comes out as 2.5%. Is that okay?
Yeah.
Is everyone clear?
When is discrete?
When is it discrete? If it's a binomial or Poisson distribution. But in this case, because you're dealing with a normal distribution, it's continuous. Yeah? Okay, good. The next one then, what about the probability that x is less than or equal to 4? Okay, so you're looking at 4 now. Well, 4 is the mean. You happy? So therefore, everything up until that point is half the distribution. Whole distribution is 100%, so half of it is going to be 50%. You can think of it that way, or you can just do 0.15 plus 2.35 plus 13.5 plus 34%. It's the same thing. Okay? Okay? And then finally, look at part D. You're looking for the probability that a value falls between -2 and what is it, 7?
7, yeah.
Okay. And you've got less than or equal to on that side. Now notice in this case, one of them's less than, one of them's less than or equal to. For a discrete distribution, that would matter. For a continuous distribution, doesn't matter. Okay? So let's have a look. So you want between -2, which is 2 standard deviations below the mean, and 7, which is 1 standard deviation above the mean. So what am I going to add together? Those three things, right?
Yeah.
So 13.5 plus 34 plus 34%, which comes out as 81.5. How did you get that? So that's 68, 78, 81.5.
81.5.
Have a look, -2 and 7, okay? So you're looking between -2 and 7. Yeah, does that make sense now? Good, yeah, so you're looking at that area there, so you're going to have to add that one, and that one together. All good? Yeah, fantastic, so 81.5. Does that make sense to everyone, like the process with how we do it? So the key thing, and I need to emphasize this because we're just about to finish off, the key thing is that you need to draw out your normal distribution first and draw it out according to this rule. So the mean goes in the middle and then you move one step each time and it's 3 steps above and below the mean. Notice, I'll move out the way in just a second then you can come and take photos. You notice that you are looking at 100% of the data. Anything beyond 3 standard deviations above and below the mean, we say the probability is so small of occurring. And that makes sense. Remember when those balls were dropping, the chance of you ending up over here or over here is really, really small. The majority of data should lie somewhere within 3 standard deviations above and below the mean. Is that okay? Yes, anything above 3 standard deviations above and below the mean, we would consider as an outlier. Okay? But can I ask you to have a look at question 2 and question 3 between now and tomorrow?